Hi everyone, my name is Cameron Williams. This is a presentation I made about my final project for Dr. Haney's Computer and Network Forensics course. My project was about extracting the firmware from the microcontroller on a hard drive. Here's a quick outline of what I'll be covering. I'll start with what motivated me to pursue this for my project in the first place and the objective I settled on after doing some preliminary research. From there, I'll talk a bit about the device that I worked with for this project, including some of the smaller components that it's made of. After that, I'll cover the tools, protocols, and techniques that I used during the project, including JTAG, the TUMPA, soldering, OpenOCD, and Ghidra. Finally, I'll wrap up by discussing some other approaches I attempted or could have attempted, some of the major takeaways and possible future work to pursue related to this, and some of the main references from my research. I originally became interested in this topic after reading a paper titled Implementation and Implications of a Stealth Hard Drive Backdoor. In the paper, the researchers discussed their experience with reverse engineering and modifying the firmware of a typical hard drive to include a data exfiltration backdoor. Their attack model consisted of a malicious actor tampering with a hard drive before it is installed into an otherwise uncompromised server. If the attacker could send some data to the server, maybe the target's a website with a form or something like that, the attacker could submit a comment containing instructions encoded for the hard drive to interpret. The modified drive could replace the attacker submitted comment with data from any block requested by the attacker, creating a data exfiltration backdoor. The research team estimated that it took them 10 months to complete the reverse engineering, modification, and testing of the firmware. And this is clearly far beyond my skill level, but I wanted to start learning a bit more about this. And with that, I kind of settled on this objective. After doing some research, it seemed like the best way to get into this area of research was to learn about JTAG. I settled on using JTAG to extract the firmware from a hard drive. At first, I wasn't sure if this would be too easy or too difficult for the project, so I decided I'd try to analyze the firmware a bit if time permitted. The device I targeted for this project was the same hard drive that I used for Project 2. It was a 320 gigabyte hard drive from Western Digital. I used a guide titled Hard Disk Firmware Hacking from malwaretech.com to guide me through most of what I did on the project. The author of the guide had a totally different model of a hard drive, which resulted in a lot of difficulty as I progressed through the project. The first thing I did with the hard drive was remove the printed circuit board from the back so that I could get a better look at what was going on underneath. This was super simple since the board was held in place by just 4 screws that were clearly visible on the back side of the hard drive. And via another source, I was able to determine what a few of the major components on the board were. The chip on the left, circled in red, is the DRAM chip, and this corresponds to the cache size of the hard drive. I was able to find a 46-page datasheet about this part from just a quick Google search. The chip on the top right, circled in purple, is the spindle motor controller. Again, a quick Google search turned up a 55-page datasheet for this part. The middle chip, circled in yellow, is the microcontroller, and that's the real target of the JTAG connection that I'll be interacting with in a little bit. Unfortunately, this part is just totally proprietary and I couldn't find any data on it. Some drives have a separate flash chip where the firmware is stored, but some have the flash memory integrated in the microcontroller, and in this case it appears to be integrated in the microcontroller. And finally, in the bottom picture, the JTAG interface is circled in orange. JTAG stands for Joint Test Action Group. It's named after the group of electronics companies that assembled in 1985 to produce a more convenient, standardized means of testing hardware. JTAG served as a replacement for the then common bed of nails testing approach, in which contact pins were placed onto a separate testing board and kind of sandwiched against the device that you were trying to test to create electrical connections for testing. This was pretty cumbersome and required a custom testing board for every single device, and that was why they started looking for ways, more effective ways of doing this. And JTAG was later codified as IEEE 1149.1 through 2013. The core of the JTAG standard is its 4 mandatory pins: test data in, test data out, test clock, and test mode select. These are typically abbreviated as they are on the slide as TDI, TDO, TCK, and TMS. There have been a bunch of extensions over the years to add additional pins for particular architectures, and the picture on the top shows a few different types of JTAG configurations, and the picture on the bottom shows the JTAG pinout from the malware tech guide that I followed. To connect my computer to the JTAG interface, I needed an adapter. I went with the same one used in the malware tech guide, the TIAO Universal Multi-Protocol Adapter, or TUMPA for short. The TUMPA supports a number of other protocols in addition to JTAG, including Serial Peripheral Interface, or SPI, Inter-Integrated Circuit, or I2C, and RS-232. The TUMPA uses a type of JTAG called 20-pin IDC. And as we'll discuss later, the TUMPA might not have been the best choice for this project. To make use of the TUMPA, I had to do some soldering. The pads on the JTAG connector of the board were really small, so I ended up using 30 gauge wires that were about 1/4 of a millimeter thick. I was worried at first I wouldn't have a steady enough hand to complete this, but it went really smoothly. And I used the continuity testing mode on my digital multimeter to make sure everything was connected as I intended. I spliced the other ends of the 30 gauge wire to some standard 2.54 millimeter jumper cables like you'd find in an Arduino kit, and this allowed me to easily connect to the TUMPA pins without making a more permanent connection. I later discovered that the pin layout on the PCB is the 38-pin Mictor connector, so I maybe could have found a cable to use that that wouldn't have required soldering, but I'd already gotten the soldering done, so it wasn't a big deal. After the soldering was done, I'd connected the jumper cables to the corresponding JTAG pins on the TUMPA. I plugged it into my Kali Linux virtual machine workstation via mini USB and powered the PCB with an AC to Molex power adapter. And at that point, I was really glad to see nothing caught fire or started smoking. I started up the OpenOCD command line utility. OpenOCD stands for Open On-Chip Debugger, and support for JTAG adapters like the TUMPA is just one of its many features. To connect to a device, OpenOCD needs a config file for the adapter in use, as well as a config for the target device. The config for the TUMPA is included in the OpenOCD install, and I used the sample config from the malware tech guide for my target device config. A screenshot of OpenOCD connecting to my target device can be seen on the bottom picture. There's a lot to break down there, so I'll cover just a few key points. Ferocion is the name of an ARM microarchitecture created by Marvell, the manufacturer of the microcontroller. My device appears to be of a different microarchitecture since it states that it expected a certain device ID but found another one. And the name Ferocion in this case was supplied by the incorrect config. The mismatch in microarchitecture is also responsible for the error with embedded ICE, which stands for in-chip emulation, and this is an important feature for debugging embedded systems. Even though I got these errors, some OpenOCD commands still worked, and this is most likely because the device I was targeting uses the same ARM v5 architecture that the Ferocion microarchitecture belongs to. When connecting to a device, OpenOCD starts listening on a few different ports, 6666 for tool command language or TCL connections, 4444 for telnet connections, and 3333 for GDB connections, and I'll get to more on this in a bit. Since the example config from the guide gave me so many errors, I tried making a few of my own. I found a list of microarchitectures that OpenOCD supports and tried using configs targeting them, but none of them worked out. I also tried using an experimental feature of OpenOCD called auto-probing that tries to automatically determine the scan chain of the target device. And a scan chain is a series of smaller devices that are located within or across multiple chips on a single board. Every config I tested, including the auto probing, had problems with establishing the appropriate scan chain. The scan chain from the example config still seemed better since it was able to open a GDB connection, so I went ahead with using that. After settling on that config, I connected to the telnet port that OpenOCD had opened. OpenOCD offers a wide variety of commands for debugging. Many that I tried spat out errors, and again, this is most likely due to the microarchitecture mismatch and subsequent embedded ICE error. One of the first commands I used that seemed to work was reset halt, which resets the processor as if it was rebooting and immediately stops it before it performs any operations. The malware tech guide suggested that this would allow me to extract the memory image of the bootstrap procedure that loads the rest of the firmware. Another command that worked was measure clock. It gave a value of about 2.4 megahertz, which I thought was kind of interesting and kind of gives a hint as to what microarchitecture might be in use if you could find an appropriate reference sheet that shows all the Marvell microcontrollers. I used the dump image command from there to create a raw binary file from the contents of the memory. I used the memory addresses supplied by the malware tech guide. I repeated this whole process from power off to create a second bootstrap.bin file as well, and I compared the hashes to see if the result was reproducible. And as you can see in the bottommost image, the hashes matched. Next, I connected to the GDB port that OpenOCD had opened. I had to use GDB multi-arch, or multi-arc, since the target device used a different architecture than my workstation. I connected using the target extended remote command. I could use some GDB commands to examine the status of the microcontroller. The result of the info registers command is depicted in the image on the right. The malware tech guide suggested that manipulating the R1 register at a certain part of the initialization process would allow for booting into different modes and capturing a full image of the microcontroller's firmware. However, it didn't seem like the reset halt command was actually stopping it before initialization, and I received an error when trying to manipulate registers. I think the no symbol table is loaded error on register manipulation was due to the embedded in-chip emulation errors that I mentioned earlier. After working with OpenOCD quite a bit, I moved on to using Ghidra. Ghidra is an open source reverse engineering tool created by the NSA. I used it to perform a very brief analysis of the bootstrap.bin file I was able to dump from memory in OpenOCD. When importing a binary file, Ghidra prompts you to select an architecture. I suspected from previous investigation that the microcontroller used ARM v5, so I tried several of the available ARM v5 variants. The variant that resulted in the most valid ARM v5 assembly language instructions after processing by Ghidra was ARM v5 Little Endian, and a sample may be seen in the image on the left. The image on the right is the code Ghidra disassembled after analysis of the bootstrap.bin. I have no good way of verifying this currently, but based on the malware tech guide and other material I researched, I think the series of if statements in the disassembly screenshot are the magic values required to initialize a microcontroller in different states. The following slide has some images of the function graph that Ghidra generated based on the bootstrap.bin file. And here they are. The left image is fully zoomed out, and the highlight at the top of the image corresponds to the highlight on the code block in the right image. I thought this was a neat feature for visualizing the control flow of the extracted binary. And that concludes most of the work that I covered in my project, but I wanted to talk about some alternative approaches to extracting the firmware that either didn't work out or I was otherwise unable to try. Your JTAG is another piece of software for interacting with JTAG adapters, similar to OpenOCD. It appears to be more up-to-date and user-friendly than OpenOCD, but I couldn't get it to work with the Tumpa, so I wasn't able to try extracting firmware this way. Some manufacturers of hard drives offer direct download of firmware updates. And this would clearly be much easier than using JTAG, but Western Digital does not offer firmware updates for the drive that I was using. Western Digital does offer a piece of software for managing firmware updates, though. This software is called Western Digital Dashboard, and there's a picture of it on the right. It may be possible to sniff traffic from a firmware update using something like USB PCAP, which is included in Wireshark. I didn't get to try this because there was no firmware update option for my hard drive in the Western Digital dashboard, but it could be an interesting approach with a different device. And finally, it's possible to read firmware directly off the flash memory on board a hard drive's PCB. I didn't try this because the flash memory on my hard drive was integrated in the microcontroller. And here are some of my final thoughts on the project. I didn't totally succeed in terms of my initial goals. I wasn't able to extract a complete firmware image from the drive, only the bootstrap.bin, if that even was what I extracted. As I said, I don't really have a good way of verifying that. I ran into a lot of problems stemming from the fact that the microcontroller was totally undocumented. It would have been much better to find a well-documented device to get started with learning about JTAG. I've read there are some decent routers and webcams that are better documented and would serve as a better starting point. The TIAO Universal Multi-Protocol Adapter may not have been the best JTAG adapter available. It might have been better to find one that's compatible with your JTAG. And finally, even though JTAG is an industry standard, there's a ton of wiggle room. There are a lot of different architectures with different pin counts, and sometimes pins with the same functionality have slightly different names, and this makes it pretty difficult to get started with for something that's supposed to be standardized. And here are the main references that I used throughout the course of my project. And thanks for listening. If you have any questions, please feel free to leave a comment or contact me directly via email or on Discord.